First of all, let me thank the organizers for organizing another virtual TQC conference, and let's hope that the next one can be held physically again. So, what will I talk about today is a result that we had last year. It's about properties of the stabilizer extent, namely that the stabilizer extent is not multiplicative, and I will explain later what this means precisely. And it's joint work with Felipe Montealegre-Mora, another PhD student from Cologne, and my two supervisors, Frank Vallentin and David Groß. Okay, so what's the outline of the talk? So first I will talk about the magic state model of quantum computation and classical simulation. Then I will introduce the stabilizer extent as a powerful tool for classical simulation algorithms of quantum algorithms. And we will not talk about how the classical simulation works. We will treat this as a black box during the talk. It's more about the stabilizer extent and its properties. And then I will come to our main result that the stabilizer extent is not multiplicative. And I will talk about implications of the result and a little bit about the proof techniques. Okay, so let's start with the stabilizer circuit model of quantum computation. So in this model, your input for your quantum algorithm is a stabilizer state. A one qubit stabilizer state is one of the 6 vertices of this octahedron inscribed inside the Bloch sphere. And the quantum operations you allow to modify your stabilizer state are measurements in the computational basis, Clifford unitaries. These are spanned by phase gates, Hadamards, and CNOTs, and you're allowed to use classical randomness and classical control. Well, this is a pretty nice model. It's well studied. It's pretty fruitful for quantum error correction, but the major drawback here is that this model can be efficiently simulated on a classical computer, and this is the famous Gottesman-Nil theorem. Okay, so how can you promote this model to universality? Well, instead of taking as an input state a stabilizer state, you take as an input a magic state, some state that does not lie inside this octahedron there. Usually the magic states that you use, well, if you consider the one qubit model, are states that lie above the facets of the octahedron or above the edges. And then you simply allow the same quantum operations to manipulate the magic state. So you allow measurements in the computational basis, you allow Clifford unitaries, and you allow classical randomness and classical control. And then you get a model that is universal for quantum computation. So this has the full power of a quantum computer. And if you want to if you want to simulate this model with a classical computer, then the runtime will scale in the non-stabilizerness of the magic input psi. Okay, people proposed a lot of different ways to measure this non-stabilizerness, and these measures are usually called magic monotones. And during the past decades, there were several proposals. So first of all, there's the Wigner function for qubits, which was introduced by Veitch, Ferry, Gross, and Emerson in 2012. There's the robustness of magic, introduced by Howard and Campbell. They work on the level of density matrices. Then there's the exact and the approximate stabilizer rank, which works on the level of vectors as the stabilizer extent 2, which was introduced in 2019 by these 6 people here: Bravi, Brown, Kolpin, Campbell, Grosset, and Howard. And there were also other proposals like the stabilizer nullity or the generalized robustness. And what do all of these magic monotones have in common? They can all be expressed in the language of optimization. Okay, so now let's make a small detour and ask ourselves, so why do people care at all about classical simulation? So, well, it's a pretty active field of research. There are kind of every month or every week, there are kind of new papers on the archive that treat this topic, that treat the topic of classical simulation. And the question you may ask is, to what extent can we classically simulate a quantum system? And classical simulation has emerged as a very important tool to benchmark the computational speedups that quantum computers can provide. So for example, if you look at the famous quantum supremacy argument experiment of Google, and there they showed that it's not possible to classically simulate what they did in their experiment, or at least they claim this. And another important point is, right now we are in the era of noisy intermediate scale quantum computers, and there if you have a quantum device and you want to verify what this quantum device does, So how can you do it? Well, if it doesn't take exponential time to simulate this this device, you could just verify it by doing the same classically. And well, this is a way how you can validate that your quantum device really does what it's supposed to do. Okay, so now let's get to the stabilizer extent after our small detour. So yeah, what do we start with? We start with a set of stabilizer states with a set of n qubit stabilizer states. So for example, for 1 qubit, these are exactly the 6 vertices of the octahedron within the blob sphere. And to introduce the stabilizer extent, we will start with the exact stabilizer rank that was introduced 3 years before the stabilizer rank. And here, what your goal is, so you have some input psi, and your goal is to express this input psi with as few stabilizer states as possible. So the goal is to minimize this number k here. And this is a very famous problem in compressed sensing and signal processing. So there, the set of stabilizer states is usually called a dictionary. And later I will also use the word dictionary, or sometimes I will also use the word dictionary for stabilizer states. And there you have a signal and you have the dictionary, and your goal is to express the signal with as few words as possible. And such a problem is an L0 minimization problem, so you want to minimize the number of words. But this is computationally pretty intractable. What do people in compressed sensing? They usually use a convex relaxation, and this is exactly what the stabilizer is for the exact stabilizer rank. So here, you take your input state psi, you express it as a linear combination of stabilizer states with complex coefficients. Now, instead of minimizing the number of words you use to express your input state psi, you simply minimize the L1 norm of the coefficients. So you minimize the absolute value of the expansion coefficients CS. And you want to make this as small as possible. And this gives rise to the stabilizer extent. So how is it defined? The stabilizer extent of an input state psi is simply defined as the minimum of the sum of the absolute values of the expansion coefficients squared. So the minimum of the L1 norm of the expansion coefficients, such that psi is expressed as a linear combination of stabilizer states. Well, this problem is a conic optimization problem. So as I've said before, it's a magic monotone, it's an optimization problem. And in this case, it's a second order cone problem, or sometimes also called conic quadratic programming problem. And these problems, they can be solved efficiently in the dimension. Well, the drawback here is that if psi is an n qubit state, then the underlying dimension is 2 to the n. So you can solve it efficiently in 2 to the n, but not in the number of qubits n. Okay, so now let's get back to classical simulation. So here, as a rule of thumb, you can imagine this as follows. So the smaller the sum of the expansion, the absolute values of the expansion coefficients is, when you express psi as a linear combination of stabilizer states, the better one can classically simulate your quantum circuit with input psi. So in a certain sense, the stabilizer extent measures the non-stabilizerness of psi. So if you need kind of a large number, like if the L1 norm of the expansion coefficient is pretty big, then psi is relatively non-stabilizer, and it's hard to simulate a quantum circuit with input psi. And the quantum circuit here is a stabilizer circuit. So you allow the operations that we've seen on the first and second slide. Okay, so as I said before, in general, the stabilizer extent is hard to compute in the number of qubits. So it's not hard to compute in the dimension 2 to the n, but in the number of qubits n. But however, the people who introduced the stabilizer extent, they showed that if you have a product state where each component is a 1, 2, or 3 qubit state, then the stabilizer extent is multiplicative. So then the extent of psi is simply the product of the extents of each single component. And well, this heavily simplifies the computation of psi, because you do not have to solve an optimization problem in dimension 2 to the n. But now what you have to do is you just have to solve k, in this case, k optimization problems in, well, dimension up to 8. So this is really a heavy simplification of the problem, because before it is kind of almost intractable for large n to compute the extent, but if I have a product state, then this gets much easier when each component is a 1, 2, or 3 qubit state. Now, well, the natural question that arises is, does this also hold for arbitrary product states? And now, as you may infer from the title, this is not the case, and this is our main result, namely that the stabilizer extent is not multiplicative in general. Okay, so what's our main result? So if I take a random n qubit state and n is sufficiently large, then the stabilizer extent is strictly submultiplicative. What does this mean? So if I want to compute the extent of psi, or more precisely, what do we do here? If I want to compute the extent of psi tensored with its complex conjugate, then the probability that this is strictly smaller than the extent of psi times the extent of psi star, then the probability that this is the case is pretty close to 1. So it's 1 minus some small constant. Well, but what our proof techniques reveal is that kind of what we do, we simply use certain properties of the set of stabilizer states, and these can be generalized to other families of dictionaries. So as I said before, usually you consider a dictionary, and in our case, these were the stabilizer states. So let's look at the informal main result that we have. So we isolate two properties of stabilizer states, and we consider an arbitrary dictionary sequence that has these two properties, and this dictionary sequence is dn. So first of all, dn is closed under taking tensor product. So if I take two words of smaller dimension and I tensor them, then I get a word of larger dimension that also lies in our dictionary sequence. And the other property that stabilizer states also satisfies that the cardinality of dn grows sub-exponentially in the dimension 2 to the n. And now we can associate an extent with respect to this dictionary sequence, and it's exactly defined as the stabilizer extent. So what do? We once again we consider some input psi. We express it as linear combination of the words in the dictionary, and we minimize the absolute values of the expansion coefficients cs and square them. And then, as you may now guess, so if you want to investigate multiplicativity of this dictionary sequence, then you will get probably the same as in the case of stabilizer states. So you should expect strict submultiplicativity. So if you tensor two states psi and phi, then and you want to compute the extent with respect to your dictionary sequence D, then you should expect that it's strictly smaller than the extent of psi times the extent of phi. And this should hold for most states. Well, maybe one important thing here, all the words in your dictionary sequence should be unit vectors, which is also the case when you consider stabilizer states, because, well, these are states, they are also unit vectors. Okay, so now let's talk a little bit about consequences of our result. So one consequence for classical simulation is the following. So suppose you know two optimal stabilizer extent decompositions of two states psi and phi. So they are given like this, and the extent is simply the L1 norm of the expansion coefficients here. Now your goal is to classically simulate a stabilizer circuit with input psi O times phi. Then you might observe the following. So your stabilizer circuit is again given by measurements in the computational basis, Clifford unitaries, and classical randomness and classical control. So if you want to classically simulate the circuit and you want to use the stabilizer extent, so what's the natural decomposition of psi tensored with phi? Well, you simply write out the expansions here, and then you get a decomposition of psi O times psi tensored phi in terms of product stabilizer states. And the L1 norm of the coefficients is given here in blue, so it's simply the sum, the product of the L1 norms that you got here. And now what our main results tells us is that this might not be optimal. So there might be a better decomposition of psi O times of psi tensored phi for classical simulation when you simply consider when you consider all 2n qubit stabilizer states, not just product states, but simply all stabilizer states. And then your classical simulation algorithm will be faster when the absolute value of the expansion coefficients on the right-hand side here is larger than on the left-hand side here. Okay, so now finally let us talk a little bit about the proof techniques that we used. So kind of the first key ingredient here is that you have to understand the underlying conic optimization problem, and we want to exploit duality because while we have a conic optimization problem, this always comes with a dual problem. Now for simplicity, we consider the case of some dictionary, and this dictionary is a real dictionary, and we consider a real input x. So then how is the extent given with respect to this dictionary? Well, here we have the square root because usually we square the absolute values. So it's the minimum over the absolute value of the expansion coefficients when we expand x in our dictionary, and now x is a real vector and d is a real dictionary, so the coefficients cs here are real. And well, what happens then, well, maybe you do not see it on first glance, but this is in fact a linear program, so not a second order cone problem, something that is even easier. And this again comes with a dual. How's the dual given? Well, it's like a classical LP. So here, what do we do? if you want to compute the extent, so we maximize in the direction of x over polyhedron, and this polyhedron, the facets of the polyhedron are given by s transposed y absolute value upper bounded by 1. So the transpose here is simply the net product. So what you do is you simply maximize in the direction of x over this polyhedron, where the facets are given by the words of the dictionary, respectively minus the words of the dictionary. And then you will end up in some vertex or some point on the boundary when you optimize in this direction. And this optimal y here is, well, especially in quantum computation, is usually called a witness. So what can you do then? Well, if you use duality, you can show the following. If I take as an input a word x tensor x, and I consider the product dictionary, so I simply consider the tensor products of words in the dictionary, then this is multiplicative. So if we define the extent with respect to d tensored with d, so it's as before, we use the dual formulation here. We're maximizing in the direction of x tensor x. That is our point that lies in this polyhedron. Then we observe that this thing is multiplicative. So if we compute this, this is simply the product of the extent of x with respect to d times the extent of x with respect to d again. And well, this is multiplicative, and if y is a witness for the extent of x with respect to d, then y tensor y will be a witness for the extent of x tensor x. And what else do we have? This optimal dual witness y tensor y is generically unique. So if we look at our picture, we are maximizing the direction of x tensor x, and generically, so you will get one unique optimal solution in the dual program. So once again, you have your polyhedron here. The facets are now given by tensor products of words of your actual dictionary, and you will, if you maximize in the direction of x tensor x, you will end up in some vertex y tensor y. So maybe one thing, maybe it's a little bit misleading here. Well, the extent with respect to this thing is not completely multiplicative. So if you take, I don't know, x and y, you cannot compute the extent of x and y for with respect to d, because the dimension just do not match. Then you do not need to observe multiplicativity here. Okay, so what do we have? If we compute the extent of x tensor x, it's multiplicative. And we have this generically unique dual witness here. Now what happens, we have this product dictionary, and now what might happen when we add a word to this dictionary. So kind of right now compute the extent with respect to a bigger set. So again, the problem is essentially the same. Geometrically, we are adding, the new word adds two new hyperplanes to our dual formulation. What might happen now, we have this dual unique witness y tensor y, and now by adding this word to the dictionary, what might happen is that this optimal unique dual witness becomes infeasible. So you can see it here in the small picture. If you add this hyperplane induced by the word W that you added to your dictionary, then this point might become infeasible here. And what happens in this case? Well, you simply decrease the extent of x tends to x when you add this word to your dictionary. So in this case, you have that the extent of this dictionary of x tends to x is smaller than the product of the extents here. And this is essentially the main idea that we use in our proof. Also in the complex case, well, in the complex case, maybe the major drawback is that you cannot draw these nice pictures anymore. But the idea remains completely the same, but you have some more technical details. And if you want to prove this generic uniqueness of this dual witness, or the analogon of the dual witness, then you use kind of complementary slackness, which is also a standard tool in conic optimization. And if your dictionary is the set of stabilizer states, then the word that you add, so the word that you add to decrease the extent, is the maximally entangled state. So this is obviously not a product state, it's a 2n qubit stabilizer state, but it does not lie in, well, it's not a product state. So here you simply do essentially the same, but what you add is the maximally entangled state. Okay, so now let's summarize our results. What have we done? We've settled an open problem about the properties of the stabilizer extent. So what does this mean? The stabilizer extent is strictly submultiplicative. So you should expect for most states psi and phi, and for most n-qubit states psi and phi, that the extent is strictly submultiplicative. And the consequence for classical simulation is the following. So if you want to search for an optimal stabilizer extent decomposition for your classical simulation algorithm, this might be hard for general product states. So if you compare this to the original result, if all your components here are 1, 2, or 3 qubit states, then computing the extent is easy. But if these components are states of higher numbers of qubits, then this might get harder. And well, kind of our proof technique really just worked with certain properties of the stabilizer states, namely the most important one that this dictionary of stabilizer states is closed under taking tensor products, and it grows sub-exponentially in the dimension. And so if you have another dictionary sequence and you want to investigate whether it's multiplicative or not, you might simply use our proof techniques to prove, well, probably strict submultiplicativity. All right, then, well, thanks for listening, and this is all of my side.